Electrical engineering exam questions. Hello everyone, welcome to my channel. My name is Rafael. I'm an electrical engineer, and this video is going to be a compilation of questions that frequently appear in exams for electrical engineers. The topic of this video is linear circuits. Let me read the first question. A multimeter was used to measure the electric current at the rightmost branch of the circuit on the board. What is the value of Vx if the instrument displays the value of 1 amp? Okay, my friends, this is the question. Let's go to the solution. Applying Ohm's law at the rightmost branch, we find VO is equal to IO, which is the current that flows here, and the instrument is displaying the value of the current, times the resistance, RO. Consequently, it is going to be 1 amp times 5 ohms, and this gives the value of 5 volts. Okay? This was easy, simply applying Ohm's law. Now let's find the currents I2, I3, and I1. To find I3, we simply divide the voltage on top of this resistor by the value of its resistance. Then it's going to be the division between VO and R3. Let's call R3. R3 is 5 ohms. And then we simply divide 5 volts divided by 5 ohms, and this is 1 amp. Likewise, we can calculate I2 as the division between the voltage VO and the value of the resistance. We're calling it R2. Then it's simply 5 volts divided by 10 ohms, which is equal to 0.5 amps. So this is a node here. This is a node. Okay? The nodal rule says that the sum of the currents that enter a node must be equal to the sum of the currents that leave a node. Okay? So I1 is the current that enters the node. I2, I3, and IO are the currents that leave the node. Consequently, I1 is equal to I2 plus I3 plus IO, which is going to be 1 amp. Okay? The multimeter is displaying the value of the current that flows here. This current here we calculated and we found 1 amp, and I2 we calculated and we found 0.5 amps. And this is 1 plus 1, 2, plus 0.5 is 2.5 amps. Okay? Then we know now all the currents that flow in all the branches of this circuit. Okay, with the value of I1, we can calculate this voltage drop here, V1. Okay, V1 is going to be equal to I1 times R1. We're calling it R1 here. And it is 2.5 amps times the resistance, which is 5 ohms. And 5 times 2.5 is 12.5 volts, okay? 2.5 amps times 5 ohms is 12.5 volts. All right? Now we know V1. And we know here that this voltage here is equal to this voltage here plus the voltage here. Okay? So Vx is equal to V1 plus VO. Okay? From here to here, VO. From here to here, V1. And they together give Vx. And then Vx is equal to V1 we calculated is 12.5 volts. And VO we calculated and we found 5 volts. And ultimately we find the value of 17.5 volts. Okay, and this is the value of this voltage source here, or if you prefer, the voltage of the power supply. Okay, my friends, this is all for exercise 1. Let's go to exercise 2. Exercise 2. A certain battery has terminals labeled A and B. And the battery voltage is 12 volts. To increase the chemical energy stored in the battery by 600 joules, how much charge must move through the battery? Should the electrons move from terminal A to terminal B, or from terminal B to terminal A? Okay, my friends, this is the question. Let's go to the solution. As a prerequisite to understanding charging, we are going to remember a case we are more familiarized with, which is the process of discharging. Consider a battery fully charged discharging through a resistor. Okay? The battery has a voltage and the resistor has a resistance. When we connect the two, a current flows here in this way. We represent the current as a flow from the positive terminal passing through the load and returning through the negative terminal. Okay? This is the process of discharging. when this happens, electrons move from the negative terminal towards the positive terminal. Okay? That is, when the battery is fully charged, there is an abundance of electrons in the negative terminal, and they migrate towards the positive terminal. This is when the battery is discharging, that is, it is supplying power to a load. Okay, now let's understand the opposite when the battery is being charged. This happens with a cell phone battery, for example. From time to time, your cell phone battery runs out of charge and you need to charge it again. Okay? You use an outlet, but the outlet is AC. And to plug your cell phone in the outlet, you do it by means of a power supply, which has a rectifier in it, which converts AC to DC. Okay? And we call this a charger. Okay? This power supply can be called a charger. Okay? But now the battery is discharged. It is not supplying power. Actually, it is consuming power. Current will flow in the opposite direction. Okay? Current will flow towards the battery, not from the battery. It is going to flow towards the battery. Okay? And electrons in this way will flow electrons will move from the positive terminal towards the negative terminal. What we want? We want an abundance of electrons in the negative terminal of the battery. Okay? And in this way, the battery is being charged. Okay, my friends, then we have understood one of the questions. To increase the chemical energy stored in the battery, electrons must move from cathode to anode. That is, from terminal A to terminal B. This is the first part of the question. Now we are going to calculate the amount of charge that must move through the battery. Okay? This charge here, these electrons here. These electrons here must move. Okay? And charge is measured in coulombs. We want to calculate how many coulombs will need to flow so the battery will be fully charged. Or, if you prefer, we are going to store 600 joules as the excess size requested. But before using the formula, let's understand how it originates. Okay? We are going to come up with the formula that we are going to use. By definition, current is equal to the division between the flow of charge by time. Okay? And from this expression, we get that Q is equal to current times time. All right, this we have understood. And how about energy and power? The relationship between energy and power is energy is equal to power times time. Okay? And since power is equal to voltage times current, we can write energy in this fashion. Energy is equal to P. Instead of writing P, we write V times I times T. This T comes here, but I times T is equal to Q. And in this way, we have come up with the expression that we are going to use to calculate the amount of charge that must move from one terminal to the other. So a energy of 600 joules will be stored. E is equal to V times Q. Ultimately, Q is equal to E divided by V. We want an amount of energy equal to 600 joules and a voltage of 12 volts. This is the rated value of voltage for this battery, 12 volts, and it gives a value of charge equal to 50 coulombs. Okay, my friends, this is the amount of charge, okay, in this case electrons, because protons do not move, okay, they must stay in the nucleus, and electrons will move. So when we talk about moving particles possessing charge, we are talking about electrons. So electrons must move through the metal, through the conductor, copper or aluminum, and we are talking about an amount of charge equal to 50 coulombs. Okay? When this happens, when 50 coulombs flow from terminal A to terminal B, we have successfully stored 600 joules of energy in the battery. Alright, my friends, this is all for exercise 2. Let's go to the next. Question 3 now. Suppose that the cost of electrical energy is 12 cents per kilowatt hour, and that your electrical bill for the period of 30 days is $60. Assume that the power delivered is constant over the entire period of 30 days. What is the power in watts? If a voltage source of 120 volts supplies this power, what current flows? If part of your electrical load is a 60 watt light, that is on continuously, by what percentage can your energy consumption be reduced? By turning this light off. Okay, my friends, this is the question. Let's go to the solution. The cost of electricity, the amount that you will need to pay, is equal to the energy that you consume times the tariff, or if you prefer, the rate. So it's energy times rate. And we want the energy. So the energy is going to be cost over rate. The cost was $60. You are paying $60 in that month. And the rate, as the exercise says, is 12 cents per kilowatt hour, dividing, we find that the amount of energy consumed in this month is 500 kilowatt hour. This is the amount of energy. Now let's calculate the power. We are supposing that the power delivered is constant. We are supposing that the power delivered is constant. Then P is going to be equal to energy divided by time. It is 500 kilowatt hour. Okay? Observe that we have the energy expressed in kilowatt hour, not in joules. So we are considering here hour. Okay, understand this unit. And for a month, 30 days times 24 hours. And therefore, the power is 694.4 watts. 694.4 watts. Let's calculate the current. The current is the division between power and voltage. The power is 694.4 watts, and the voltage, the exercise says that it is 120 volts, and this gives a current of 5.78 amps. Now let's measure the reduction. The exercise said that the power of the light is 60 watts. So the reduction will be 60 watts divided by the total power, 694.4 watts times 100%. And it is a reduction of 8.64% if our light is on continuously, and if we turn this light off, there will be a reduction of 8.64% in our electrical bill. Okay? This is all for exercise 3. Now let's go to exercise 4. Question 4. A fully charged deep cycle lead acid storage battery is rated for 12.6 volts and 100 ampere hours. This battery is used aboard a sailboat to power the electronics, which consume 30 watts. Assume that the battery voltage is constant during the discharge. For how many hours can the electronics be operated from the battery without recharging? How much energy in kilowatt hour is initially stored in the battery? If the battery costs $95 and has a service life of 250 charge-discharge cycles, what is the cost of the energy in dollars per kilowatt hour? Okay, my friends, this is the question. Let's go to the solution. The current supplied to the electronics is current is equal to power divided by voltage. Okay? The exercise said that the power consumed by the electronics is 30 watts, and the exercise also said that the voltage the battery supplies is 12.6 volts. And in this way, by carrying out this division, we find that the current is 2.38 amps. Okay? The ampere hour rating of the battery is the operating time to discharge multiplied by the current. The operating time is T equal to 100 ampere hour divided by the current, 2.38 amps. Do you understand here? The battery can deliver this amount of current, 100 ampere hour, okay, until it is fully discharged. And the current that the battery is actually delivering is 2.38 amps. Okay, so dividing the capacity by the actual current, we get that the battery delivering this current is going to be able to operate for 42 hours. Okay, the battery can deliver 100 ampere hours, and since the battery is supplying 2.38 amperes, it will be able to operate for 42 hours. All right. The energy initially stored is going to be E equal to the power times the operating time. Okay? The power is the amount of energy per second. Okay? This is the definition of power. The operating time is the amount of time, or the period of time, the battery will be operating since it is being required to deliver this amount of energy. So this amount of energy for the period of 42 hours exceeds or is precisely equal to the capacity of the battery. Okay? Then it is going to be 30 watts times 42 hours, and this gives 1.26 kilowatt hour. And the cost of energy for 250 cycles. The cost is equal to the price of the battery. The exercise said that the battery cost $95, and we have 250 cycles divided by the amount of energy, 1.26 kilowatt hour. Okay, 1.6 kilowatt hour is the amount of energy that can be stored in one charging. Okay, but if we charge and discharge 250 times, the amount of energy will be 250 times the amount of energy in one charge. If we divide the cost of the battery by the total amount of energy in its service life, we get a cost of 0.3 cents per kilowatt hour. Okay, this is a parameter used in engineering to assess whether it is feasible or it is cost effective, there is going to be a good return on the investment. Okay, we calculate the amount of energy that a battery can store in its entire life, and we divide the total price of this equipment by the total energy, and we have this estimate. And we do the same for every technology. This technology here is lead acid. We could have lithium ion and other battery technologies, and we divide the price of the equipment by the total energy that it is going to store in its service life. And for example, this technology is 0.3. There may be some technology that is 0.55 per kilowatt hour. some technology may be 8.7 per kilowatt hour, then the more cost effective, where you are going to have a better return on investment, is going to be the one that has a lower price per kilowatt hour. Okay? Do you fully comprehend? So my friends, this is all for exercise 4. Let's go to exercise 5. Question 5. The figure shows the electrical model for an electronic megaphone, in which the 16 ohm resistance models a loudspeaker, the current source and the 5 ohm resistance represent a microphone, and the remaining elements model an amplifier. What is the name of the type of controlled source shown? Given that the power delivered to the 16 ohm resistance is 16 watts, determine the current flowing in the controlled source. Also determine the value of the microphone current Ix. Okay, my friends, this is the question. Let's go to the solution. This is a voltage controlled current source. What does it mean? See that this is a current source, and the current is a function of this voltage. Okay? When the current source is a function of a voltage, we understand this as a voltage controlled current source. That is a current source that is controlled by a voltage. Alright, now let's calculate the other parameters. If the power, the exercises say that the power delivered to the load is 16 watts, okay? If the power delivered to the load element is 16 watts, and let's regard this VO. We are calling this voltage here on top of the load resistor VO. And power can be calculated as current squared times the resistance. But current is voltage divided by resistance. So VO divided by RO squared times RO. And this is VO squared divided by RO. Okay? PO, the output power, is equal to VO squared divided by RO. And from this, we find an expression of the output voltage as the square root of RO times PO. Okay? And using the values, instead of RO, I use 16 ohms, and instead of PO, I use 16 watts. And of course, we find 16 volts, all right? Then we found this. Let me put it here. We already found this 16 volts. Let's find the other parameters. We are going to find now the current here. Okay? There is a current here. All right? This current here, a VI, is equal to this current plus this current here. And how do we express this current and this current? Simply by the division between the voltage and the value of each resistance. 32 ohms plus VO divided by 16 ohms. All right? This current here that enters this node must be equal to the sum of the currents that leave the node. And by using the value, okay, 16 volts, 1 over 32 plus 1 over 16, we find the value of 1.5 amps. This is the value of the current of this voltage controlled current source. So AVI is equal to 1.5 amps. Let's find the other parameters. The exercise gave the value of A as 25, okay? The amount of amplification is 25. And A times VI is equal to 1.5 amps. That is 25 VI is equal to 1.5 amps. Dividing 1.5 by 25, we find that the value of the input voltage is 60 millivolts. Okay? VI or Vin, if you prefer. VI or Vin, if you prefer. For me, it's the same. 60 millivolts. And what else can we calculate? We are going to calculate the current of the current source, Ix, In the same way, we calculated this current here, or these currents here. We simply do the following. Let me erase it here. I need more space. And Ix, the current here, is equal to the sum of the currents here and here. Okay? This current here is V in divided by 5 ohms, and here 2 ohms. And using the value of V in that we just found, we discovered that the value of the current source is 42 milliamps. Okay? And this is all for exercise 5. Let's go to exercise 6 now. Question 6. Reduce the network shown on the board to a single equivalent resistance by combining resistances in series and parallel. Okay, my friends, this is the question. Let's go to the solution. Firstly, we are going to work on the parallel connection between these two resistances here, 15 ohms and 60 ohms. Okay? And the rule that we are going to use is the product over the sum. We are going to call this combination here equivalent resistance number 1. The equivalent resistance number 1 is going to be equal to 15 times 60 over 15 plus 60. Okay? The rule of thumb for combining resistances in parallel is the product over the sum. And this gives 12 ohms. Okay? And now let's hide it here. The equivalent resistance number 1 is going to be in series with this resistance here. Okay? So the equivalent resistance number 2 is going to be 12 ohms plus 6 ohms, and this is 18 ohms. All right. The equivalent resistance number 2 is in parallel with this resistance here, 9 ohms. Okay? It goes, this equivalent resistance goes from this point to this point. Okay? This pole, this node to this node. Alright, so equivalent resistance number 3 is going to be the parallel connection between equivalent resistance number 2 and 9 ohms. And the rule of thumb that we are using is the product over the sum. 18 times 9 over 18 plus 9. And this is 6 ohms. And this equivalent resistance number 3, will be now in series with this resistance here, 6 ohms. And equivalent resistance number 4 is 6 ohms plus 6 ohms, which is 12 ohms. And this 12 ohms will be from here to here, and thus in parallel with this resistance here. Then equivalent resistance number 5, is the parallel connection between 24 ohms and 12 ohms. The product over the sum. And if we remove all this, we observe that equivalent resistance number 5 is in series with 5 and 10 ohms. They will be in a series connection like this. Okay? And we just sum them. The total equivalent resistance is going to be 5 plus 10 plus 8, which is 23 ohms. Okay? My friends, this is all for exercise 6. Let's go to exercise 7. Question 7. Letter A. Find the voltages V1 and V2 for the circuit shown on the board by combining resistances in series and parallel. Letter B. Suppose that the value of Vs is adjusted until V1 is 10 volts. Determine the new values for V2 and Vs. Okay, my friends, this is the question. Let's go to the solution. First of all, letter A. We are going to combine resistances until there is only one equivalent resistance. Alright, immediately we can see that there is a series connection between these two resistances here. 5 plus 25 is 30. Okay, so the equivalent resistance number 1 is equal to 25 plus 5, which is 30 ohms. And they together are in parallel with this resistance here. Okay? And for combining resistances connected in parallel, we use the rule of thumb, which is the product of the sum. Okay? It is going to be like this. Equivalent resistance number 2 is the product over the sum. And the 30 times 30, divided by 30 plus 30 is 15. Okay? And we are going to erase all this, and the resulting equivalent resistance is this. And this equivalent resistance number 2, is in parallel with this 10 ohms. We are going to combine then. (15 times 10 divided by 15 plus 10), okay? When combining resistances in parallel, we use the product over the sum. And we find a value of 6 ohms. And this 6 ohms is going to replace all of this, okay? Observe that this 6 ohms is in series with this 6 ohms and these 12 ohms. They are in a series connection, okay, across the voltage source. Then the total equivalent resistance is going to be 12 plus 6 plus 6, which is 24 ohms. Okay? This is the total equivalent resistance. And now let's calculate the output current of the voltage source. The voltage source is going to supply current, and we are going to use this equivalent resistance to calculate it. It's going to be the voltage of the voltage source is 12 volts. And the equivalent resistance is 24 ohms. The current is therefore equal to 12 volts divided by 24 ohms. And this is equal to 0.5 amps. Alright? 0.5 amps. This is the current of the source. This is the current of the source. The current that the source delivers. Let's find now the other quantities. We're going to find now V1. There is a resistance here, which is an actual resistance. There is a resistance here, which is an actual resistance. And this 6 ohms here is not an actual resistance. This is a value that arose from our calculation of the equivalent resistance. And it is 6 ohms. And on top of it, V1. Okay? V1 is equal to 0.5 amperes. The current that flows here, 0.5 amperes times 6 ohms, which is 3 volts. Observe that V1 is 3 volts, but you must not use 24 ohms to calculate V1. You may think, oh, V1 is here. Why not calculate V1 here using 24 volts? No, because 24 volts is taking into account all these resistances here. 6, the equivalent resistance, and 12. There is a voltage drop here, a voltage drop here. So, to calculate V1, you must not use this resistance. You need to use this resistance here. Alright, then V1 is 3 volts. Now let's calculate V2. We are going to apply the voltage divider rule. That is the circuit here. We don't need to worry about what is here. All we need to know is that V1 is here, and here we have 25, and here we have 5. Okay? Applying the voltage divider rule, we obtain that V2 is equal to 5 over 5 plus 25 times V1. Okay? And using the value of V1, we calculated and discovered the value of 3 volts. We find that it is equal to 0.5 volts. Okay? In this manner, we have answered the question. We have found the solutions. Okay? V1 is 3 volts and V2 is 0.5 volts. Now let's calculate letter B. In letter B, V1 is 10 volts. And we need to determine V2 and Vs, provided that V1 is 10 volts. Okay? We are requested to adjust the voltage of the power supply. So V1 is 10 volts. Now the exercise asks us, what is the value of V2 and Vs if V1 is 10 volts? Okay, this is what we are going to calculate. We can immediately find, let me use some labels here. I'm gonna label this current here I2, okay? And I'm gonna label this current here I3. And there I4, okay? We can immediately calculate I2 and I3 based on the value of V1 and the resistances. I2 is equal to 10 volts divided by 10 ohms. Okay? And this gives a value of 1 amp. Likewise, I3 will be equal to 10 volts divided by 30 ohms. And I3 is 0.333 amps. Okay? Again, applying the voltage divider rule, okay, we have something of the sort. We have something of the sort. We know that here is V1. And we have here $25 and $5. Okay? We do not need to worry about what is here. To calculate V2, it is enough to know the value of V1. We apply the voltage divider rule and we find that V2 is equal to 5 divided by 5 plus 25 times V1, and this gives a value of 1.67 volts. What else? We can calculate the value of the current of the source in this way here. I1. Let me call it I1 here, okay? Because we have already labeled the current of the source in a different way for letter A. For letter B, we are going to call it I1. We know that the sum of the currents that enter a node must be equal to the sum of the currents that leave the node. We know that there is a node here, okay? From here to here there is a node. And the current that enters the node is I1. I1 is entering the node. And the currents that leave the node are I2, I3, and I4. Okay, so I1 is I2 plus I3 plus I4. And we already know their values. We know that I2 is 1. We know that I3 is 0.333. And we need to find I4. I4 we haven't yet calculated. It is easy. I4 is simply the division between the voltage V1, okay? The voltage here we know that it is V1, and the sum of the resistances here is 30, so it is 10 divided by 30, and it is 0.333 amps again. So we have two currents of equal value here, and I1 will therefore be 1.67 amps. All right? And what else? To finish, the exercise wants us to calculate the value of the voltage of the power supply that makes V1 be equal to 10 volts. And this value can be found as Vs, not Vx, Vs Vs is equal to I1 okay. Let's understand what we are calculating here. There is a voltage drop here, okay? This current here is going to flow here. There is a voltage drop here. And there is a voltage drop here. And this voltage drop here we already know, and it is V1. So, I1 times 12 ohms plus 6 ohms, okay? I1 while passing here will cause a voltage drop, and the value of this voltage drop is I1 times 12. And while passing here, I1 causes a voltage drop, and the value of this voltage drop is I1 times 6. So the combined voltage drop will be I1 times 12 plus 6 plus the value of V1, okay, plus V1, and this is 40 volts, okay. We have understood, this is the conclusion, that when we adjust Vs to the value of 40 volts, V1 becomes 10 volts. Okay, my friends, this is all for exercise 7. Let's go to exercise 8. Question 8. We want to store sufficient energy in a 10 millifarad capacitor to supply 5 horsepower to an automobile for 1 hour. To what voltage must the capacitor be charged? Does this seem to be a practical method for storing this amount of energy? Do you think that an electric automobile design based on capacitive energy storage is feasible? Okay, my friends, this is the question. Let's go to the solution. Our first step will be to convert the power from horsepower to kilowatts. It is then P equal to 5 HP times the converting factor. Okay, we are going to convert from this system, HP, to kilowatts. And the converting factor is 745.7 watts per horsepower. And this gives an approximate value of 3.73 kilowatts. Okay? This is the power that we are going to supply to the automobile. And the energy, we want an amount of energy in 1 hour, okay? An amount of energy that is capable of supplying for 1 hour this amount of power. The energy will be power times time. The power is 3.73 kilowatts, and the time is 1 hour is equal to 3600 seconds. Okay, 3600 seconds. Why seconds? Because power is expressed in seconds. Okay? and using the International System of Units, power in watts and time in seconds, we get joules. So this is equal to 13.42 times 10 to the 6th joules. This is the amount of energy that needs to be stored in this 10 millifarad capacitor, so we will be able to supply 3.73 kilowatts of power for 1 hour to the automobile. Have you fully comprehended? Since we are talking about a capacitor, we have to use an expression that embodies the characteristics of capacitors, okay? And we are going to find the voltage that the capacitor will have. This kind of capacitor here, 10 millifarad. We are going to begin by understanding that P of t is equal to V of t times I of t. Okay? For a single phase element, P times I, V times I is equal to P. Okay? In the capacitor, current flow is proportional to the derivative of the voltage. We know also this, that for capacitors, the current is proportional to the derivative of the voltage with respect to time, and the constant of proportionality is the capacitance of the capacitor. And we are going to combine these two expressions here, this and this. Okay? So the power will be expressed as C. We are going to put this here in the place of I. C equal to V of t times the derivative with respect to time of V of t. Alright? If the capacitor is initially discharged, okay, V of t equal to 0 plus is equal to 0. We are assuming that the capacitor is initially charged. We will understand that energy is equal to the integral from t0 to t1 from the initial point in time that we are considering to any kind of point in time, and it is the integral of the power. Okay, this is the definition. This is the broadest definition of energy. Okay, it is the integral with respect to time of the power. And we are going to express power in this way here. Okay? For us here, power is equal to C V of t, the derivative with respect to time of the voltage, dt. We can confidently cancel this out and express energy in this manner here. The integral from the initial point in time to t of c v of t dv of t. Okay? All right? Integrating this, we find that the energy is a half of C times V of T squared. We find this expression in reference textbooks in electrical engineering or in physics as E equal to CV squared over 2. From this expression, we find that V is equal to the square root of 2E over C, where C is the capacitance of the capacitor, E is the energy that will be stored in the capacitor, and V, the voltage of this capacitor after this amount of energy is stored there. Alright, and if we use the values that the exercise gave, okay, we know that our energy is this, okay, the capacitance is this, 10 millifarad. Using these values here, we find a voltage of 51.8 kilovolts. Okay? 51,000 volts. 51.8 kilovolts. This is very dangerous for an automobile. This is the conclusion that we need to take from this. We are going to conclude that this is extremely dangerous for an automobile. Anybody that touch it will be seriously injured. And the conclusion is that it turns out that a 10 millifarad capacitor rated for this voltage would be much too large and dangerous and massive for powering an automobile. Besides, for a reasonable performance, an automobile would need much more than 5 horsepower for 1 hour. Electric automobiles nowadays work with powers much greater than this, so we need more horsepower. This is not enough. This is not enough. And the voltage is very big and dangerous. So we need a different way. We need a different way to power an automobile. Not use this kind of capacitor. Okay, my friends, this is all for exercise 8. Let's go to exercise 9 now. Question number 9. If the initial voltage across the capacitor is 0, VC of t equal to 0 plus 0 volts. Find an expression for the capacitor voltage as a function of time and sketch. Alright, my friends, this is the question. Let's go to the solution. For all t, Vs is equal to Vr plus Vc. Okay? The voltage of the source is equal to the sum of the voltage drops across the resistor and the capacitor. Let's write this as a function of time. Vs of t is equal to R times I of t plus 1 over C times the integral of I of t dt. Observe that the voltage of the source is DC. This is a DC power supply. Okay? The derivative of a constant is 0. Okay? So the derivative with respect to time of Vs of t is equal to 0, and this is equal to R times the derivative with respect to time of I of t plus I of t over C. Okay? This enables us to conclude that the derivative with respect to time of I of t is equal to the negative of I of t divided by RC. The next step is to pass this dt here and this I of t here. So it is going to be d I of t over I of t, and this is equal to 1 over RC dt. In this way, we can integrate. We are going to integrate both sides. And they differ only by a constant of integration. The integral of this must be equal to the integral of this, okay? and the difference is only a constant of integration, okay? Because the derivative of a constant is 0, and the derivative of all this, including the constant, and this, the derivative of this, will have to be equal, okay? Because this is where we come from. We come from where they are equal, but they can be equal, and when integrating they can differ, but the only difference will be that of a constant value. That's why we consider this constant of integration. And we find that ln I of t is equal to minus t over rc plus k, and I of t will be equal to k times e to t over rc. Okay, this is the value of the current. Let's store this here. Let's save it here, because this is the most important result. And I'm going to clean the board for more expressions that we need to consider. At t equal to 0 plus the current I of t equal to 0 plus is equal to k. We are going to put 0 in the place of t, and this has to be equal to immediately after the switch turns on, okay? The switch moves from off to on. When this happens, precisely at 0 t, the capacitor behaves as a short circuit, okay? Then the current at t equal to 0 plus will be simply the division between the voltage of the battery and the resistance R. And this gives a value of 1 milliamp. Okay? And since e to 0 is 1, we find that the value of k is 1 milliamp. We are calling it K1, okay? K1. Because, I don't know, maybe we will need to integrate again and find another K. So, let's call it K1. K1 is 1 milliamp. And the expression for the current becomes I of t equal to 1 times e to t over RC milliamps. Okay? To find the capacitor voltage, we need to use the property that we know. We know that Vc of t is equal to 1 over c times the integral of I of t dt. Okay? The voltage across the capacitor can be found by integrating the current. And it is going to be 1 over c times the integral of e to negative t over RC. Okay? And here, I'm going to use 10 to the negative 3 because it is milli. Okay? Milli 10 to the negative 3. Amp. Let's continue with our integration. It results in 1 over c times 1 milliamp or 10 to the negative 3 amps times this integral here results in RC times e to negative t over RC plus another constant of integration. We are calling it K2. And Vc of t is going to be, let's cancel this with this, okay? And here we have current. Here we have resistance. Resistance times current is voltage. Okay? And this is equal to Vs. But negative Vs E minus T over RC plus K2. Okay? We are almost there. We need to find the value of K2 now. How do we do it? Let's consider the initial condition. At t equal to 0, the capacitor behaves as a short circuit. And in this way, Vc of t equal to 0 plus is equal to negative Vs times e to 0. Okay, we put 0 in the place of t plus K2. And this has to be equal to 0 volts because we have understood that at t equal to 0 plus the capacitor behaves as a short circuit. And in this regard, we find that K2 is equal to Vs, and the expression of the capacitor voltage is Vc of t equal to Vs 1 minus E negative t over Rc. Okay, this is the expression of the capacitor voltage. And the time constant of this expression here, considering a connection with a resistor, because a capacitor needs a resistor to discharge. That's why the value of the resistance appears in the expression of the capacitor voltage. All right? And the time constant, RC, is equal to 10 to 5 times 0.01 times 10 to the negative 6, and this is 1 milliseconds. Now let's plot it, the exercise wanted us to sketch it. We have here the voltage axis, and we have here the time axis, okay? And let's put time in milliseconds. And here the voltage at 1 milliseconds here, 2 and 3 and so on. We have here 100 volts. Okay. And this is the value of the capacitor voltage. Okay? This is how the capacitor voltage behaves. It is initially discharged and it is going to charge in this way. Alright, my friends? And this is all for exercise 9. Let's go to exercise 10 now. Question 10. The dielectric materials used in real capacitors are not perfect insulators. A resistance called a leakage resistance in parallel with the capacitance can model this imperfection. As here, okay? A 100 microfarad capacitor is initially charged to 100 volts. We want 90% of the initial energy to remain after 1 minute. What is the limit on the leakage resistance for this capacitor? Okay, my friends, this is the question. Let's go to the solution. From the previous exercise, we know that the capacitor voltage while discharging through a resistance is, in the previous exercise, we calculated for charging. Now it is being discharged. Okay? The exercise said that the initial voltage is 100 volts. And that the capacitance is 100 microfarad. Continuing, the energy stored in a capacitor can be calculated using the expression E is equal to a half of C times VC squared. Okay? We are going to use the values that the exercise gave. Okay, it is going to be equal to a half times the value of the capacitance, 100 microfarad times VI 100 V squared times e to negative 2t RC. And the initial value of this energy, okay, at t equal to 0, is equal to EI, the initial value of the energy, 0.5 joules. We want 90% of the initial value of the energy stored to remain after 1 minute. So 90% of EI has to be less than or equal to the amount of energy that we are working with, and the amount of energy that we are working with is 0.5 times e to negative 2t over RC. And 1 minute is 60 seconds. For t equal to 60 seconds, okay, we are going to work with SI units, the international system, okay, joules, ohms, farad, and for time we use seconds. And 1 minute is 60 seconds. 0.9 is less than or equal to divided by RC, and applying the logarithm, from this we get that RC, this product, the resistance times the capacitance, has to be greater than or equal to 1139. Since we know the value of the capacitance, we conclude that the resistance must be greater than or equal to 11.39 mega ohms, okay? If we want the initial energy stored, regardless of the amount, we see that we cancel the amount of energy out here with this, okay? So regardless of the initial energy, in this case it was 0.5 joules, but regardless of the amount of energy, for this kind of voltage, we are going to have 90% of the initial energy still there after 1 minute if the leakage resistance is greater than or equal to 11.39 mega ohms. Okay? And the leakage resistance must be greater than this value. Alright, my friends, this is all for exercise 10. Let's go to exercise 11. Question 11. Consider the circuit on the board. What is the steady state value of the capacitor voltage after the switch opens? Determine how long it takes after the switch opens before the capacitor voltage is within 1% of its steady state value. Okay, my friends, this is the question. Let's solve it. Observe that before the switch opens, there is a short circuit here. Can you see? Therefore, the entire current of this DC current source passes through the branch of the switch, and no current goes to the other side. However, after the switch opens, we put an end to the short circuit and the current goes to the resistor and the capacitor, and after the circuit reaches steady state, the capacitor behaves as an open circuit. Okay? In steady state, the capacitor will behave as an open circuit and all the current will flow through the resistor. Okay? So in steady state, VR, okay, the voltage on top of the resistor will be equal to the current of the source. The current of the source does not have any other way to flow. We have opened it here, and the capacitor is behaving as an open circuit. The only way will be to pass through the resistor. So it is 10 milliamps times the resistance of the resistor, and this is equal to 10 volts. As the resistor is in parallel with the capacitor, this is also the capacitor voltage at steady state conditions. Therefore, one of the questions, what is the steady state value of the capacitor voltage? We have already calculated it. Let me write it here. Vc of steady state is equal to 10 volts. Okay. Now let's analyze the transient. Let's analyze the transient. Immediately after the switch opens at t equal to 0 plus, the capacitor behaves as a short circuit. Okay? You see that if the capacitor is completely discharged, then it is easy to put charge on the capacitor. It is difficult to put charge on the capacitor if the capacitor is already very much charged. So, in a steady state, the capacitor behaves as an open circuit. However, immediately after we open the switch, the capacitor behaves as a short circuit. And we can confidently say that Vc at t equal to 0 plus is equal to 0 volts. Okay? The time constant of the circuit is, okay, let me put it here to not forget. Vc of t equal to 0 plus is equal to 0 volts. And the time constant of the circuit will be the multiplication of the resistance and the capacitance. Rc is equal to 1 kilo ohms times 10 microfarad. And this is equal to 10 milliseconds. And the capacitor voltage as a function of time while charging, okay, while charging, because here, if we open it here, okay, if we open the circuit here and isolate the capacitor and the resistor from the current source, the capacitor would discharge through the resistor. However, if we connect the current source, instead of discharging, the capacitor is actually charging. So, the capacitor voltage as a function of time when it is charging is Vc of t is equal to 10 times 1 minus e raised to the power of 100t. To be within 1% of its steady state value after, how long does it take? We actually want t. We want t. We want t for 1%. 1%. We want t for 1%. We want to determine how long it takes after switching before the capacitor voltage reaches 99%. Okay, we want to stay within 1% of its steady state value. In other words, we want at least 99% of the full charge. Okay, so to be within 1% of its steady state value, Vc has to be equal to 9.9 volts, because the steady state value is 10 volts, and if we want to be at least within 1% of its final value, the final value will be 9.9 volts. Okay? So 9.9 volts has to be equal to 10 minus 10e negative 100 t. And manipulating and applying the logarithm, we find that negative 2 ln 10 is equal to negative 100 t. And then we find the value of 46.05 milliseconds. And let's interpret this result. The interpretation is that it takes roughly 46 milliseconds for the capacitor voltage to reach 99% of its steady state value. Okay? This is exercise 11. Let's go to exercise 12 now. Question 13. Consider the circuit on the board. Solve for the steady state values of I1, I2, I3, I4, and Vc after the switch has been closed for a long time. Okay? Initially, the switch is open. If the switch is open, there is nothing here. Okay? There is an inductor here, but it is not going to hold magnetic field because there are resistors in the circuit. And resistors have this capability of consuming energy. They convert electrical energy into heat. And the same for the capacitor. If the capacitor is initially charged and it is connected to a resistor, the energy stored in the capacitor will be consumed by the resistor. It is going to be converted into heat. So we are not interested in the case where the switch is open. We want to analyze the situation in which the switch is closed, but not the transient. We want steady state. The exercise wants us to analyze the case for which the switch has been closed for a long time. Okay? If the switch is closed for a long time, then the circuit reaches steady state in this situation here with the switch closed. Let's begin analyzing. in a circuit powered by a DC source, this is a DC source, in steady state, okay, in steady state, the inductor behaves as a short circuit. There is an inductor here in steady state. After a long time has passed, the inductor behaves as a short circuit. And how about the capacitor? In steady state, capacitors behave as open circuits. Okay, this is our first analysis. Consequently, this circuit here can be redrawn as, I'm going to redraw the circuit for steady state. So only in steady state, the circuit becomes this. The power supply the 50 ohms resistor this branch here is open because, as we concluded, the capacitor behaves as an open circuit, and here we represent only the resistance because the inductor is behaving as a short circuit. Consequently, we have this voltage here. Observe that this voltage here is on top of all elements here, okay? Okay? This voltage here, 100 volts, is applied here. Alright? It is the same. It is here and it is there. In this way, I4 is going to be equal to 100 volts divided by 50 ohms. And this gives a value of 2 amperes, or if you prefer, 2 amps. We know that I3 is 0 because the capacitor is behaving as an open circuit. I2 is 100 volts divided by 100 ohms, and it is equal to 1 amp. And I1 is the sum of the currents because we have a node here. Okay? The current that enters the node is equal to the sum of the currents that leave the node. So I1 is equal to I2 plus I3 plus I4, and this is equal to 3 amps. Alright? 3 amps. And now we need to calculate the steady state value of the capacitor voltage. Since I3 is 0, okay, we have 100 volts, the voltage of the power supply here as well. and the capacitor voltage is equal to 100 volts. And in this way, we've found all the solutions. The solution for the currents and the capacitor voltage. We have calculated everything. Okay, my friends, this is all for exercise 13. Let's go to exercise 14 now. Question 13. Find the RMS value of the current waveform shown on the board. And the period here is 2, here is 4, here is 6, and here is 8. We can see that the period is 4, okay? 4 seconds. The period is 4 seconds. The RMS value of this current can be calculated as IRMS is equal to the square root (1 over the period) times the integral from 0 to the period I of t squared dt. Observe that the value of current from 0 to 2 is 5, and from 2 to 4 is negative 2. We're going to use it. We need to split it apart because we have different values. From 0 to 2 is 5, and from 2 to 4 is negative 2. Okay? Then it is going to be a fourth of the integral from 0 to 2 of 5 squared dt plus from 2 to 4 negative 2 squared dt. Okay? And it can be further reduced to 2 the square root of a fourth, 25 times 2 plus 4 times 2, and ultimately we find that the value of the RMS current to be equal to 3.808 amps. Okay? We can approximate it to 3.8 amps. This is the RMS value of the current. Okay? Observe that it is different than the peak value. The peak value is 5. But when calculating power, we do not use the peak value of a signal. In reality, the peak value is not 5 because we have to split it in half to find the peak value. The peak value is going to be 5 plus 2 divided by 2, which is 7/2, which is approximately 3.5, precisely 3.5. But anyway, this current here is not equally divided here. For example, 3.5, 3.5. No. Okay? It is not like this. This axis here does not exist. It is -2 here and 5 here. So that's why the RMS value of the current is 3.8 amps and the positive peak 5 and the negative peak -2. Okay, my friends, this is all for exercise 13. Let's go to exercise 14 now. Question 14. Consider the circuit shown on the board, composed of a current source, a resistor, an inductor, and a capacitor. The exercise wants us to find the phasors for IS, IR, IL, IC, and the V. And the exercise also wants us to compare the peak values of IL and IS and explain the result. Okay, my friends, this is the question. Let's go to the solution. Firstly, we are going to find the phasor for IS. The phasor for IS is equal to, we represent phasors as capital letters with a dot on top, and it is going to be 10 phase 0 degrees milliamps. Okay, and observe that the angular velocity is 10,000 radians per second. W is equal to 10 to the 4th radians per second. Okay, with the value of the angular velocity, W, we can calculate the impedance of the capacitor and the impedance of the inductor. Observe that the impedance of the inductor is equal to J times the inductive reactance, and the inductive reactance is equal to JWL. If we use the value of the angular velocity and the inductance, we find J 200 ohms. This is the impedance of the inductor. Likewise, we can find the impedance of the capacitor, and the impedance of the capacitor is -J XC. Okay, -J XC. And it can also be expressed as -J 1 over WC. And this gives a value of -J 200 ohms. Okay? This is the impedance of the capacitor. Now, let's find the value of this voltage here. Okay? To find the value of the voltage, we're going to understand that IS, the current that enters here, has to be equal to the sum of the currents that go down here. Okay? And this is equal to IR plus IL plus IC. Okay, IS is going to be equal to V 1 over 1 kilo ohms plus 1 over J 200 ohms minus 1 over J 200. Okay? And manipulating this and using that IS is 10 phase 0 degrees milliamps, we find that V is equal to 10 phase 0 degrees volts, okay? Then we have already calculated two of the parameters that the exercise requested from us. Is is equal to 10 phase 0 degrees milliamps, and V is equal to 10 phase 0 degrees volts. Alright? Now we are going to calculate the currents, the phasors for these currents here. IR is equal to V, the value of the voltage, divided by the resistance of this resistor here, and we find that IR is equal to 10 phase 0 degrees milliamps. Now the value of IL is equal to V divided by the impedance of the inductor divided by J200, and this gives a value of 50 phase negative 90 degrees milliamps, okay? Observe that there is a shift, okay, of 90 degrees between the angle between the inductor, the current of the inductor, and the current of the resistor. And IC is going to be V divided by negative J200, and this is 50 phase 90 degrees milliamps, okay? The current in a resistor is in phase with the voltage. The current in an inductor, the current lags the voltage, and in a capacitor, this is a capacitor here, in a capacitor, the current leads the voltage, okay? One more time, the current is in phase with the voltage for a resistor, the current lags the voltage for an inductor, and for a capacitor, the current leads the voltage. Alright? And what did the exercise want us to analyze? Oh, I remember, it was the peak value. Observe that IL is 5 times larger than IS. IL is 50 and IS is 10, okay? And this phenomenon happens because the capacitor behaves, the capacitor current balances, the capacitor current balances the inductor current, okay? You see that the current through the resistor is this, the current through the inductor is this, and the current through the capacitor is this, okay? But much larger, alright? They balance each other out and they cancel each other out. That's why instantaneously, okay, for a brief period of time, provided that they cancel each other out, the current of the inductor can be larger than the current of the current source. That's the explanation, my friends. And we observe here that IL plus IC is equal to 0. They cancel each other out. This is all for exercise 14. Let's go to exercise 15. Question 15. Determine the power for each element, including the sources for the circuit shown on the board. There are two power supplies, one resistor and one inductor. Also state whether each element is supplying or consuming energy. Okay, my friends, this is the question. Let's go to the solution. Firstly, we will work on the current, okay? The current phasor. Observe that we are taking source A as a reference. Source A is our reference. And we are considering the current as supplied by source A, okay? The current goes from source A to the other elements, including source B. We could have chosen the opposite. We could have chosen the current I as flowing from source B to the other elements, okay? And this option here is wrong. No, it is not. It is not wrong. The difference is that when taking source A as reference, some quantities will appear with a negative sign and the positive sign. And if we take source B as reference, the quantities that appeared with negative sign will appear with positive sign, and the quantities that appeared with positive sign will appear with negative sign. But the magnitude has to be kept the same, has to be the same, okay? And we will need to understand the results based on these negative and positive signs as taking source A as reference, okay? Let me do it, and then I am going to tell you what I'm talking about, okay? So the current will be 240 phase 60 degrees minus 280 phase 30 degrees divided by 5 plus J8, okay? When calculating power, and we will need to calculate power, we do not use the peak value. We use the RMS value. Okay, and in this way, we find a current of 14.84 phase 93 degrees amps. Okay. The current of the circuit, taking source A as reference, is 14.84 phase 93 degrees amps. Okay, now let's calculate the powers. The exercise wanted us to calculate the powers. Let's calculate for source A first. Source A, the complex power of source A, okay, with a dot on top. Without the dot, it is the apparent power. With the dot on top, it is the complex power, is equal to the multiplication between the voltage phasor and the complex conjugate of the current phasor. The complex conjugate of the current phasor. And VA is 240 phase 60 degrees, and the current we just calculated, I erased it, and I'm going to write it again. It is 14.84 phase 93 degrees. Okay? We are going to work with the complex conjugate of the current phasor. Instead of using the angle of 93 degrees, we use the angle negative 93 degrees, okay? So, this is the complex conjugate of the phasor, 14.84 phase and negative 93 degrees. Using these values, we find that the complex power of source A is 3.56 phase negative 33 degrees kVA. All right. And how about the real power, or if you prefer, some people like to call active power. How about the real power, PA, without the dot, okay? Without the dot. This is a complex quantity. This is not, okay? This is a scalar, a real number. I want to make a real number. And this is equal to SA without the dot times the cosine of negative 33 degrees, okay? This is not this. This, the apparent power, is the magnitude of the complex power. The complex power has magnitude and angle. And this is 2.99 kilowatts. And now let's calculate the reactive power. Q A is equal to the apparent power times the sine, negative 33 degrees, and this is equal to minus 1.94 kV kVAR. Kilovolt ampere reactive. Okay, so these are the powers for source A. And what can we say about this? As PA is 2.99 kilowatts, it means that source A is supplying real power. Okay? We conclude that source A is supplying real power. And as we need to understand from the perspective of the current, the reference is from source A to source B. Source A is supplying real power, but source A is not supplying real power. Okay? As the current is from source A to source B, and I find a negative number here, it means that source A is actually consuming reactive power. Okay? This negative sign here, taking the reference of the current from source A to source B, means that source A is actually consuming reactive power. Okay, Now let's calculate the same parameters for source B. For source B now, the complex power of source B with a dot on top is the multiplication between the voltage phasor and the complex conjugate of the current phasor, and we use this value here. And the current, we do not use the actual current, we use the complex conjugate of the current, and we find a value of 4.15 phase negative 60 degrees kVA. Okay? And this is SB phase. Let me call it this angle here, B. Okay? The complex number here has a magnitude and an angle. The magnitude of the complex number is, for the complex power, the magnitude is the apparent power. We're going to use the apparent power to calculate the real power, or active power if you prefer. And it is the apparent power times the cosine of negative 60 degrees, negative 63 degrees, and it is equal to 1.89 kilowatts. And for now we are going to calculate the reactive power, and the reactive power is calculated as the apparent power times the sine, negative 63 degrees, and we find a negative 3.7 kVAR. Okay. Observe that the current is in this direction here, from source A to source B. When we find a positive number here, it means that the source B is actually consuming real power. Source B is actually consuming real power, okay? Because it's behaving as a load here when we have this reference. And if we had found here a positive sign, it would also mean that it is consuming, but not. In reality, we see that this negative sign here means that power is flowing in the opposite direction, in the negative direction of the current, which means that source B is actually supplying reactive power. Okay? This positive sign here means that source B is consuming real power, and this negative sign here means that source B is supplying reactive power. Okay? This seems difficult because of the reference of the current. When we take the reference of the current from A to B, we have different values of positive and negative signs, different polarities here. When we take from source B to source A, we find the same values, okay, the same numbers, but where it is negative, a positive sign may appear, and where it is positive, a negative sign may appear. indicating the change of polarity of direction of the currents that we've taken as reference. Let's calculate now for the resistor. For the resistor, the resistor does not consume nor produce reactive power. The resistor only consumes real power. So it is going to be I squared times R, which is equal to 1.1 kilowatts. Okay, so our conclusion is that the resistor is consuming real power, and the inductor does not consume or produce real power. The inductor only consumes reactive power. So for the inductor, we have that the QL is equal to I squared times the inductive reactance, and this gives a value of 1.7 kVAR. All right? So the resistor is consuming real power, and the inductor is consuming reactive power. And this is all for exercise 15. Let's go to exercise 16 now. Question 16. Find the real, reactive, and apparent power supplied by the source. This is the source. Find the power factor seen by the source and state whether it is leading or lagging. This is the question, my friends. Let's solve it. The voltage of the power supply is this, and we know that W is equal to 400 radians per second. And with this value of W, we can calculate the reactances. Okay? The impedance of the inductor is equal to J XL, and the inductive reactance is J 400 times 0.25 Henry, and this is equal to J 100 ohms. Okay, this is the impedance of the inductor. Now the capacitor, in the same way, ZC is equal to negative J XC, which is equal to negative J 1 over 10 millifarad times 400. And this gives a value of negative J 250 ohms. Okay? And now let's calculate the powers. The real power is going to be consumed by the resistor, nor the inductor or the capacitor consume real power, only the resistor. So for the resistor, P is equal to the voltage, okay, 1500 squared divided by 25 ohms, okay? voltage squared divided by resistance is the real power consumed by the resistor, and it is equal to 90 kilowatts. Now the power consumed by the reactive elements, you're gonna have here the circuit, okay? We're gonna have here the circuit. The inductor and the capacitor in parallel, and to combine impedances in parallel, we use the rule of thumb, the product over the sum. So the equivalent impedance is J100 times negative J250 divided by J100 minus J250, and this is equal to J166.7 ohms. From the value, look at this. This is positive. This combination here of the inductor and the capacitor gives a positive value for the equivalent impedance. If you observe the capacitive impedance, it is negative, and if you observe the inductive impedance, it is positive. What does it mean? It means that the inductive side of this parallel connection prevails, is prevalent. So the combination between this inductor and this capacitor is more inductive than capacitive, okay? The inductor prevails, and there is a positive sign here. And the load consumes 13.5 kVAR, okay? If we use for the reactive power, we're gonna use squared divided by 166.7, and then we find a value of 13.5 kVAR, okay? And this has to be negative. This has to be negative because, no, this has to be positive. This is positive, okay? And now let's calculate the apparent power. The apparent power is going to be the square root of P squared plus Q squared, and it is 91 kVA, okay? And to calculate the power factor, it is going to be P over S, which is P. Where is P? 90 as 91, and we find 0.99 lagging. So it is a lagging power factor. And my friends, this is all for exercise 16. Let's go to the last, exercise 17. Question 17, the last. Two loads A and B are connected in parallel across a 1 kilovolt or ms 60 Hz line as shown on the board. Load A consumes 10 kilowatts with a 90% lagging power factor. Okay, load A 10 kilowatts, 90% lagging, while load B has an apparent power of 15 kVA with an 80% lagging power factor. Okay? Find the power, reactive power, and apparent power delivered by the source. We want to find these quantities for the source. What is the power factor seen by the source? Okay, my friends, this is the question. Let's solve it. Firstly, we are going to calculate the powers for each load. All of it for each load. Load A, let's calculate the powers for load A. The exercise said that the real power, or if you prefer the active power, for load A is 10 kilowatts. And the exercise also said that the power factor is 0.9 lagging. Okay, what does it mean? It means that this is an inductive load. For inductive loads, the current lags the voltage. Okay? We are going to calculate the complex power, which is equal to the apparent power in an angle. Okay? And this angle is the inverse cosine of the power factor, and this is equal to 25.8 degrees. All right? And since we know that the real power is equal to the apparent power times the power factor, okay? Or if you prefer, the cosine of this angle here, we can calculate the apparent power, okay? The apparent power S, the real power divided by the power factor, and this gives a value of 11.11 kVA. Okay? This is the apparent power, and with the apparent power, we can calculate the reactive power. The reactive power is going to be the apparent power times the sine of the angle and Using the values, we find 4.84 kVAr. Alright? And the complex power is 11.1 phase, 25.8 degrees kVA. This is all for load A. Let's do the same for load B. We only erase here, here, okay, it's better if we erase everything here, okay? The exercise said that the apparent power 15 kVA, okay? The apparent power consumed by load B is 15 kVA, and that the power factor is 0.8 lagging. Again, this is an inductive load, okay, for which the current lags the voltage. And as we have from the power factor, we find the angle. The angle is the inverse cosine of the power factor, which is 36.87 degrees. Okay? In this way, the complex power is equal to the apparent power in an angle, and for us, the real power is going to be equal to the apparent power times the power factor, and it is equal to 12 kilowatts. In this way, we find the value of 15 phase 36.87 degrees kVA. And using this angle again, we find that Q is equal to the apparent power times the sine of the angle. Okay? The complex power delivered by the source can be calculated either by summing the individual complex powers or by using the real and reactive powers. Okay? The real power delivered by the power supply will be the reactive power supplied by the source is the sum of the reactive powers. And to find the total apparent power supplied by the source, we use this expression. (26 kVA). This is the apparent power supplied by the source. And the power factor seen by the source is okay? And our conclusion is that both loads A and B have lagging power factors. They consume reactive power. If one of the loads had a leading power factor, it would be supplying part of the reactive power consumed by the other loads. Okay, my friends, this is the video that I wanted to make. I hope you enjoyed watching the video and learned from it. I am a teacher, my friends. If you want to contact me and book a lesson, I am going to leave my WhatsApp number in the description of the video, and you are free to contact me, my friends. Goodbye!